So in the previous lecture, we derived the expression for the probability of error in the probability of the decision rule making an error, and we saw that of course, in the presence of additive white Gaussian noise, we saw that the expression for the probability of error is given in terms of the Q function as we derived E1 plus E0 by 2 minus rho root E0 E1 divided by N0, and E1 and E0 correspond to the energies of the two signals S1 and S0T, S1T and S0T, and these two signals correspond to the hypothesis H1 and H0 as we discussed earlier already. Rho is the correlation coefficient between the signals S1 and S0T, and N0 by 2 is the two-sided power spectral density of the additive white Gaussian noise. Now we take a couple of examples, and we will see how this depending on the signals rather S1T and S0T, how these various terms which appear here, how these various expressions, what will be the energy and the correlation coefficient and so on and so forth. And we will take an example, and we will take some signals S1 and S0, and we'll see. So let's take the first example. Now here, let's say that S1T is a signal like this. S1T is a signal like this. This is 1 millivolt, and this is minus 1 millivolt, let's say. And let's say that the duration of the signal is 1 millisecond. And this is 0.5 milliseconds. So S1T is such that it stays at 1 millivolt from 0 to 0.5 millisecond, and minus 1 millivolt from 0.5 millisecond to 1 millisecond. And this corresponds to capital T, which is the signaling interval or the observation interval. And S0T is, say, 1 millivolt from 0 to 1 millisecond. So it stays flat at 1 millivolt from 0 to 1 millisecond. Let's say these are the two signals. And let's say that we are told that the two-sided power spectral density of additive white Gaussian noise is 10 power minus 10 by 2 watts per hertz, which means that, very simple, N0 is equal to 10 power minus 10 watts per hertz. So let's say that this is the given data. Now let's calculate what is the probability of error. If the system is such that when hypothesis H1 is true, S1T is transmitted, and when hypothesis H0 is true, S0T is transmitted, and the transmitted signals are corrupted by additive white Gaussian noise, which has a two-sided power spectral density, which is N0 by 2 equal to 10 power minus 10 by 2, 10 power minus 10 divided by 2 watts per hertz. So we need to calculate the energy first. So let's calculate the energy, because that's what we have to plug in here, the energies, and then we have to calculate the rho, the correlation coefficient, and not is anyhow given. So let's calculate the energy E1. E1 is equal to integral 0 to t, as you know, S1 square t. The signal is real, so I can simply square it and integrate it from 0 to t to get its energy. And when I see that capital T is 1 millisecond, 10 power minus 3 seconds, and when I square S1 square, I get throughout 1 millivolt. I get throughout 1 millivolt square. That means 10 power minus 6. It will be 10 power minus 6, because 1 millivolt is 10 power minus 3 volt. So when I square it, I get 10 power minus 6 volt square. And as you know, we take the resistance as 1 ohm. These are all basic things which you should be knowing. And now, of course, it's minus 1 millivolt here, but you are squaring it since it's S1 square T. So it's quite simple. So this will turn out to be 10 power, as you can see, 10 power minus 6 T, the result of integration, 0 to 10 power minus 3. You get the result as 10 power minus 9 joules. That will be the value for E1. Right. And similarly, we calculate, so remember this, and we similarly calculate E0, 0 to T. T is again 1 millisecond, and S0 square will be 10 power minus 6, because it's 1 millivolt throughout, and the result will be the same as this. So that means E1 is equal to E0 is equal to 10 power minus 9. So we can substitute that here. E1 is equal to E0 is equal to 10 power minus 9, and this as a whole will be 10 power minus 9, because E1 plus E0 gives you 2 into 10 power minus 9, and you are dividing it by 2, so you get 10 power minus 9. Now we have to calculate rho. So rho is equal to 1 by root E1 E0, 0 to T S1 T S0 T. Again, the signals are real, so nothing to worry about conjugation and the order of conjugation, and the order in which they appear here, of course. And this will result in 1 by root E0 E1. We know the values of E0 and E1, but let's have it there as it is. Integral 0 to 0.5 milliseconds, that is 0 to 0.5 to 10 power minus 3 seconds, and in that interval S1 into S0 gives us 1 millivolt into 1 millivolt, which is 10 power minus 6 plus 0.5 into 10 power minus 3 seconds to 10 power minus 3 seconds, and in this interval S1 is minus 1 millivolt, S0 is 1 millivolt, so we get it as minus 10 power minus 6 dt, that is minus 1 millivolt into 1 millivolt, that will be minus 10 power minus 6, and the result will be, whether you substitute these values or not, the result will be 0. As you can see here, 10 power minus 6, and the interval is the same, minus 10 power minus 6, this interval is also the same, so the result will be a quantity minus the same quantity, you get the result as 0. So now when we substitute over here rho as equal to 0, we get it like this, and N0 is given to be 10 power minus 10, which will be 10 power 10, which results in 10, and square root of 10 one can find out is something like 3.16. Q of 3.16. This is the probability of error, and you can use the Q table which is available. You can find that in standard textbooks, or you can get it from the net. You can see that this result is approximately equal to 8 into 10 power minus 4. This is the probability of error. If you can solve this problem on your own. If you get a different answer, if you feel that I made a mistake somewhere, please mention it in the comments and we will discuss that. Now we take the next example. We'll take a second example now. And remember that in the subsequent discussions, when we discuss the modulation schemes, we'll be using this expression straight away to find out the probability of error of different modulation schemes. Now let us take the second example and say S1t is equal to cos 4 pi t by capital T, where capital T is that capital T, the signaling interval or the observation interval, the signaling duration, whatever you call it. And let's say S naught T is minus cos 4 pi t by capital T. So S1t, if I plot, S1t, you can see that in the interval 0 to t there will be 2 cycles. In the interval 0 to t there will be 2 cycles. So it's a rough sketch of S1t, t by 2, t by 4, 3t by 4. So it's a rough sketch. There will be 2 cycles, and as you can see, when t is 0 it is 1, t is equal to t by 4 you get minus 1. So this is a freehand sketch which will look somewhat like this. There are 2 cycles. So this is S1t. Now S0t is just the negative of S1t. So that will also have 2 cycles, but it will go like this. It's a freehand sketch. Yeah, this is how it will be. So blue is S0t. And as you know, this will be 1 unit, volt or ampere, whatever it is. This will be minus 1. So maybe we can call it as volts. And now E1 will be the energy of S1. The E1 will be 0 to t. We are not given the value of t, so we stick to the variable itself, 0 to t. S1 square will be cos square 4 pi t by t dt, which we can write using basic trigonometric relations as 1 minus cos 8 pi t by t divided by 2 dt, which turns out to be, because this integration, when you integrate this over t, you will have 4 cycles of this, 4 complete cycles of this in this duration, so the result will be 0, and hence the result of this will be just t by 2, because only 1 by 2 effectively you will be integrating only 1 by 2 from 0 to t, and you get t by 2. And in the same way you can see that E naught will be so since you are squaring S naught t, this negative sign will become positive, you'll end up getting exactly the same. So E1 is equal to E naught. In this case also, as it was earlier, E1 is equal to E naught, and in this case it's equal to T by 2 units. T by 2 units. Now we calculate rho. Now we calculate the correlation coefficient. Rho is equal to 1 by root E naught E1, that will be square root of t square by 4, even E naught is t square by 4, which gives us 2 by t. Integral 0 to t s1t into s0 t, that will give you minus cos square 4 pi t by t dt, and we already know the result of this, which is as t by 2, which is equal to t by 2. We have done the same thing here, so we get t by 2, which is minus 1. So rho is minus 1 in this case. That means the probability of error will be Q. If you recall, first term here is E1 plus E0 by 2. That will be T by 2 plus T by 2 by 2. That will be T by 2. And then we had minus rho. So rho is minus 1. So minus of rho will give you plus, because rho into, and you have root of E0 E1, that will again be t by 2, because root of E1 into E0 will be root of t square by 4, which is t by 2, and rho being minus 1, that negative sign becomes plus divided by N0, and this turns out to be t by 2 N0. So if we have the values of N0 and t, we can plug it in here and find out numerically what is that number. We can find out what is that number, which gives us the probability of error. So if you have observed it carefully, it's a very simple thing, nothing much to observe here. In fact, this example corresponds to a digital modulation scheme. Of course, we'll be discussing more later. This corresponds to a digital modulation scheme, which we call as the BPSK, the binary phase shift keying. S1 signal S1t is a sinusoid. S0t is another sinusoid, the same sinusoid with a negative sign, or in other words, it is 180-degree phase shifted compared to S1t. So with these two examples, we will now move on to a discussion on developing the receiver schematics, because so far what we have discussed is how on paper, theoretically, mathematically, how this optimum decision can be taken when it comes to the hypothesis, the binary hypothesis, of course, being represented by two different signals, and we have also derived the error probability expression, but we have not yet discussed anything about the receiver schematics. That is how actually we will implement this decision rule in a real system. And a schematics is the first step towards that. Once we have the schematics, we can, of course, the hardware engineer or the firmware engineer can decide how to build the receiver. So let's move on to that. So we'll discuss the receiver schematics now. Now, a short while ago, we saw that the probability of error in that numerical example, the second example which I worked out, the probability of error was q square root of t by n naught. The final answer was q square root of t by n naught. So while I was recording the lecture, by mistake I had missed out the square root sign, as well as in addition to missing out the square root sign, I had a 2 in the denominator, and I have used some graphics and hidden that 2, and also the square root sign I have been able to include using some graphics. So please bear with that, because if it happens in a live classroom, usually some student will point it out and I will get a chance to correct it. But here what happened is I saw that after I recorded it. So that's why I had to do some editing there and correct it. I was too lazy to record it again. So anyhow, the final answer is this for the previous example, the last example. Now, continuing further, we will now develop the receiver schematics, as I said a short while ago. So what we do is we observe, we understand that we go step by step in the development of the receiver schematics. We start with the expression for R1. You should be knowing what is R1 by this time. That is, random variable is capital R1, and this is a sample value which it can take, 0 to t. RT, this is the a sample function of the random process RT which is received, capital RT which is received, into phi 1t dt. We know that this is how we arrive at R1, and we also know that phi 1t, if you recall, earlier we had shown that phi 1t is equal to s1t by root e1. So this gives us R1, and we can write it like this. Similarly, R2 is RT into phi 2t. Now earlier we saw that phi 2t is equal to s naught t minus rho root e naught phi 1t divided by square root of e naught 1 minus rho square. So remember that the signals, we still treat the signals as real signals, dt of course. And phi 1t we already know is s1t by root e1. So this will be s1t by root e1. So that I will include here by writing this as square root of e naught by e1. And of course I can write this now as 1 by square root of e naught 1 minus rho square. So we have this with us. Now what we do is we will substitute these expressions for R1 and R2 in this, and you should be familiar with what I am writing here now. R1 into, within brackets, root of E1 minus rho root of E0 minus R2 square root of 1 minus rho square E naught. This is the random variable gamma which we compare with, of course, as I said, you should be remembering this, but just for a quick recollection, this is the random variable which we compare with the threshold gamma t, gamma subscript t, where gamma subscript t is n naught by 2 natural log p naught by p1 plus e1 minus e naught by 2. So I will not write that down. Anyhow, you know, this is what we compare with the threshold. So this is the random variable gamma which we compare with the threshold gamma t. So what we do is we will substitute R1 here and R2 here. We substitute that, and when we substitute it over here, I don't know whether I have enough space here to do that, but I will try nevertheless. So I will write R1 here, one by one I will write. So I'll substitute for R1 here, 1 by root E1. This is a simple substitution which you can yourself do and verify. RT S1 t dt. So I have substituted for R1 minus, I have to have now square root of 1 minus rho square E naught into R2. So into R2 is here, fairly long. Let's see whether we can fit it in this space. This term, an integration from 0 to t, and I have to write this now. So RT into, I think I may end up cramming, but okay, let's see, minus rho root E naught by E1 S1 t dt. Yeah, I think that is legible enough to see. Right, now you can see that when you expand the brackets, of course these will cancel each other, and probably I can write like this will cancel each other, and we will get something like this when I divide both of these terms with root E1. Now if you see, you have, we don't need this now, so I will use this space. So if you see this now, we see that there is minus rho root E naught by E1 into integral 0 to t RTS1 t dt, and we have the same thing here in the form of minus into minus plus rho root E naught by E1 S1 t into RT dt. That means this, I should not cut this because that will confuse. So what I should actually be removing is this. So this will go, in the sense this will become 0, this term will vanish, this term will vanish. What I am trying to say here is that I am trying to put it here by skipping some steps. Minus rho root E naught by E1 into this integral will cancel, will eliminate itself when it encounters minus into minus plus rho root E naught by E1 S1 t into RT 0 to integral 0 to t. So that term vanishes, which means that in this, from this first term, what we have to really carry forward is, this will become 1, What we have to really carry forward is only this. Because this term becomes 1, this term will vanish because it will cancel with the second integral here. There are two integrals here actually. They are written as a single one within a single integration sign, but they can split it into two. And from the second integral, we saw that anyhow this has got cancelled. So what we have to carry forward is, so basically this is what it ends up. When you expand the brackets and cancel the terms, you end up getting this, which incidentally can be written as we can write it like this. And this tells us, in fact, what we have here, if you remember, is when we started off with this, what we had in our minds was the random variable gamma, which we compare with threshold. That is what has become like this. So we can say the random variable gamma is this. And this tells us how to arrive at the schematics of the receiver. So what this tells is that having received a sample function RT, where RT can be S1T plus noise or S0T plus noise depending on which of the two hypotheses is true. So having received RT, you just have to multiply. This is a multiplier. You have to multiply it with S1T minus S0T, which means that you should be having the signal S1T as well as S0T in your receiver. You must be able to generate the signal S1T as well as S0T in your receiver. And that's possible because you know what is S1T and S0T in advance. You have to generate an exact replica of S1T and S0T in your receiver locally. So you need to have a local signal generator which can generate S1T and S0T and subtract them and get S1T minus S0T. Then after that you have to integrate the signal so obtained within the interval 0 to t. I can write it integrate from 0 to small t, and then so this part till here what it does is RT into this and integrate, and then at the end of the integration interval you just sample. So we can also write it like this. So you integrate it from 0 to small t, and when small t is equal to t, at that time you just sample the output. You will get the result as exactly equal to gamma, and then give that as an input to your decision circuitry or the decision device. Set the threshold as gamma t, and if as earlier gamma is greater than gamma t means h1, otherwise h0, or gamma is greater than gamma t means s1t, otherwise s0t, and then you have the decision here. So this is the receiver schematics. So if you could build this, you have the receiver in hardware or firmware or whichever way it is. Now since the receiver should have a local copy of signal S1T and S0T, an exact version of S1T and S0T, we call this type of receiver as a coherent receiver. It's called as a coherent receiver because an exact copy of S1T and S0T should be available. So if S1T and S0T are sinusoids, then the frequency as well as phase of the S1T and S0T that you have generated at your receiver should exactly match the frequency and phase of S1T and S0T used by the transmitter. So you should have a coherent copy version of the signal S1T and S0T as the one used by the transmitter at your receiver. You must be able to have that. You should have it in your receiving circuitry or in your receiver if this has to work, this schematic has to work. So hence it is called as a coherent receiver. This coherent receiver schematics. Now in the same breath I have to add that there is an equivalent to this there is an equivalent to this, which is as given here. So this is the coherent receiver schematics. Now the equivalent is like this. Having received R of t, you simply pass it through a filter which has an impulse response equal to S1 capital T minus T minus S0 capital T minus T. Pass it through a filter like this, and the filter output you sample at t is equal to t, and you will end up getting the same random variable gamma, and the rest of it, of course, pass it through a decision circuitry and take a decision. So we can have decision circuitry, threshold given, and all those things. Now these two are equivalent receivers, and it can be proved very easily. It can be proved very easily because we know that from elementary linear circuit analysis, we know that the output of this filter will be a convolution between RT and HT. That will be the output of the linear filter in time domain, and we can write that convolution through the convolution integral like this. R tau, that is the letter tau, H t minus tau d tau, and since your observation interval, the signal R of t exists only in the interval 0 to t, your observation interval is this, so your limits of integration will be this, and ht minus tau, since we know this is ht, I can write ht minus tau as equal to S1t minus t minus tau, t plus tau, sorry, minus S0 t minus t plus tau t tau. So remember, this is h t minus tau. So wherever there is t, we put t minus tau to end up getting this. And you are integrating it at the end of the integration interval, that is, you integrate it at t is equal to capital T, not at the end of the integration interval. I apologize for that slip of the tongue. You sample this result at small t is equal to capital T. You sample it at that time instant when the small t is equal to capital T, and you will end up getting, when you set t as equal to t in this, you are sampling the output of the filter at t is equal to t. When you set it as equal to capital T, so exactly the sample you get will be this. And if you see, this is a number actually, because it's a definite integral, you get a number, and that number will be t minus t is 0, so we just have tau. T minus t is 0, so you will just have tau. And you can see that this is exactly the same as what this is doing, and hence this will be gamma, which is given to this. So you can see that these two perform the same task. Here you are doing it through an integrator and you're doing it through a multiplier and an integrator and then sampling the output. You get the same result if you pass the received signal through a filter which has an impulse response like this and then sample the output at the right time. You get the same result. Now this is called as a coherent receiver schematics, as I said, and there is a name for this. It is called as the matched filter receiver schematics. They are equivalent. They are equivalent in this context. And what exactly is a matched filter? A matched filter is the one which maximizes the SNR at its output. When its input is a signal which it is matched to, and it is combined with additive white Gaussian noise. So the derivation of a matched filter is actually a very good example of the application of an inequality. So I have given the link to a video in the description of this video. You can see in that video, you can see the derivation of the match filter. I'm not including it here because it is something that is done at the undergraduate level, so I will not include it here. But remember that this filter, which has its impulse response S1 capital T minus T minus S0 capital T minus T, is actually said to be matched to the signal. So this filter is matched to the signal S1T minus S0T. So a filter which is matched to a signal, say xt, a filter which is matched to the signal xt, which exists from 0 to t, will have its impulse response as equal to x t minus t. So as I said, there is a link to a video in the description of this video. You can find that below. If you see that video, you'll see that how the match filter is derived and how it is becoming an interesting application of an inequality. So with this, we end the discussion on signal detection and very basic detection theory. And again, I emphasize the discussion has been limited to such topics which are of relevance to the type of digital communication systems that we'll be discussing in the subsequent lectures. And in the next maybe couple of lectures, we'll be discussing some basic estimation theory. So in the beginning, I don't remember whether I told what is the difference between detection and estimation, but okay. So detection part is over. So in the next few lectures, maybe a couple of lectures, we'll be discussing the estimation theory, again from the perspective of the type of digital communication systems which we'll be discussing.